Otherwise, I'm going to skip right to 7.6. What value is angular momentum? L. So L can be negative L, sorry, 0 to n minus 1, right? And m sub L, which is negative L to positive L, right? Allowed for the principal quantum number of 3. N equals 3. L value has to be substituted in here. 3 minus 1, which is 2. So these three numbers. And a 0 is an S, always is the same. That's a P and that's a D. And then the M sub L, each one gets its own. So this is a 0. This is negative L to positive L. This is a negative 1, 0, and 1. The negative 2, negative 1, 0, 1, and 2. And that means that this one has one orbital. These aren't actually numbers, it's just orbitals. This has 3 orbitals. So P has 3, S has 1, and P has 5. Getting some background stuff right there. That's going on. There we go. Let me get rid of that. All right. So then we'll do the other side. Actually, how many orbitals are allowed for n equals 3? Number of orbitals is equal to n squared, or 9. In this case, because 3 squared is 9. And then number of electrons in an energy level is going to be double that, because you can have 2 electrons in each. That's 18. And I can see in the 9 by going 1, 2, 3, 4, 5, 6, 7, 8, 9, or I can just shortcut it with that, n squared. All right, so that's kind of quick. Let me know. We'll go over the stuff you need. All right. And then it says give the name, magnetic quantum number, and number of orbitals for each of the following quantum numbers. So already n equals 3, so we know the energy level is up front, and that's 2. So let's list our L values. 0, 1, 2, 3, and so on, right? S, P, D, and F. These are the only ones that exist for ground states with both energy levels. But if you somehow got these numbers, then you would just follow the alphabet after F. So this one's a 3, and L equals 2 is a D. That's a 3D. And this one's going to be a 2 up front because the N, and then 0 is S. And then last, C will be 5, right, which will be the same. And then 1 is the L value, which is P. And then you do this one. If it's confusing to you, let me know. Okay, stop the actual tape and do that. All right, the video. The tape. How old am I? All right, what's wrong with each of the following quantum designations and their sublevel names? Okay, so this one says 1, 1, 0, and 1p. This is a problem right off the bat because when we do n equals 1, okay, the L value should be 0. This is only an S shape. So the first n level is small, so it only has an S shape. So this number is not even a possibility. Right? Because it should be just 0. It's the only one it has. So then this can't be true, but this is correct based on the information in front of it. So I would say this is the wrong mark. The next one, n equals 4. L values can be 0, 1, 2, and 3, S, P, D, and F. So that's still okay. And if I do F, right? 3F, it goes -3, -2, -1, 0, 1, 2, whoops, 2, and 3. So that means I have 1, 2, 3, 4, 5, 6, 7, which I should have. And this +1 is a possibility. It's still on the table. And then 4D. Well, this is 4F. It's a 3 there, right? So that's not possible. Okay. And then the last one, you do, and see if you can figure out what's wrong with it. Let me know. You can email me at any point in time. It's totally fine. All right. We're going to skip and we're going to come back to this. So I'm going to go ahead and explain something as we go forward. We'll see if it makes sense. Okay. Write a set of quantum numbers for the third one. All right. Ready? Here, we're going to do. We are going to do electron configurations. Right? And orbital diagrams. We're going to start with the smallest element in the periodic table. Well, I need you to get a periodic table and mark all this crazy stuff on it, right? So you can stop it. Oops, where's that? So you can stop it and mark all this stuff on there for me. All right, picture. Okay. So what we're going to do is we're going to do hydrogen first. And we're going to do its electron configuration, its address. Okay. So we're going to identify which one's specifically hydrogen. And if we take a look at a simple model of the atom, okay, the first level is n equals 1, and that's what it means, that n equals 3. Okay. And so when in our ground state, we always want to go towards the lowest level, called the off ball. Fill lowest and by closest to nucleus energy levels first. That's the off ball. And so if hydrogen was there, it would have one electron sitting out over here. That's where it would be. It's called the ground state. Low energy. So we have 1 here. We want to figure out its location. It's in the first energy level, so we'll say 1. And before we said n equals 1, so the L values can just be 0. So it only has one possible shape, that's S. And we're literally going to count how many electrons we have. We have 1. That's the electron configuration for hydrogen. Now, from that, we can also write what we call an orbital diagram, which is a line, basically. And in that line, you can put electrons. So in this case, it'd be 1 electron here. 1s with 1 electron there. Kind of the diagram. We got to fix something on it later, but we're not going to worry about it yet. All right, let's do another one. Carbon. Okay, so carbon has 6 electrons. We're going to fill the bottom ones first. That's the lowest bucket. That's off ball. So we put 2 on the inside. We put 4 on this next level. So that's 6 total. Filled from the bottom up. We got to fill the middle one first and go from there. So I got all these markings on this thing, which you stopped, looked at for a second. And we're going to look at carbon, which is here. You can see that it's a p orbital, and it's in the second period, right? So it's a 2p, and we're going to count over in the p's, 1, 2. The carbon ends in 2p2. That, right? But the off-ball principle says I got to fill the springs that are lower in energy in first. So if this is carbon, then I got to fill these in over here, which is 2s, 1, 2. And let's fill the top level in as well. The numbers that are lower, I got to fill in 1s2. So we end up with this. 1s2, 2s2. Then 2, 4, 6 for carbon. Now here's the orbital diagram. 2 electrons in here, that's the 1s. 2 electrons in here, that's the 2s. So the p has 3 orbitals, right? So this one's going to be 2 electrons, or 1 electron here and 1 electron there. That, where it doesn't double up first, we got to put 1 in each first. It's called Hund's rule. Okay? We're rolling now. All right. So let's talk about something else for a second. Quantum numbers. Okay? Give us the address of the electrons. Okay? And because of that, we have something called the Pauli exclusion principle. It states that no 2 electrons can have same 4 quantum numbers. Okay? No 2 electrons can have the same 4 quantum numbers. So these have to be different. So we have 3 already. We have N, L, M sub L. Right? And this is the energy level. So it's the biggest one. It's like the state of Michigan, right? This is the shape, like Livonia, right? We're getting lower. This is the, it's called the orientation. We're going to call it the orbital, right? And then the M sub S is the last one. It's called spin. And it is the separation between the last 2. I'll show you what I mean in a second. Okay? So then we end up with this one being a positive half, or a negative half. That's the values you can have for it. So let's go ahead and do one. And we'll start simple. We're going to do helium. Okay? He. And I moved He over on my periodic table to this spot for today. Because even though it's a noble gas, it's totally filled. It's the first energy level, has just an S level in it. There's 2 electrons that can fit in it. And that's why it's here. It doesn't react because all the electrons in the outside are filled. It fits better what we're doing today in this box because it's in the 1S and there's 2 of them. So 1s2. That's helium. We'll draw the orbital diagram. 1, 2. Okay, so this is a 1s. Right? Now, if I want to know the address on this electron, okay, I need its 4 quantum numbers. So I need N, L, M sub L, and M sub S. Now, the easiest one to get is the 1 right there. That's the big one. That's the N, right? And then another one that's easy to get is the S. If we looked at it, our L values can be 0, 1, 2, 3, S, P, D, and F. So if that's an S, that's a 0. Now, the next easiest one is this one's going up. So it's a positive half. We're just down to the last one, right? And if we do the N equals 1, L equals 0, M sub L, you just have 0 value. It only has 1 orbital. That's what the M sub L represents, right? And there's only 1 of them, and it's 0. If we did the other one, it's exactly the same, but its last number is slightly different. Right? They can't be exactly the same, or you would never be able to distinguish which one's which. It's kind of like having the same address. You order all this stuff from Amazon, it never gets to your house because your neighbor has the exact same address. Okay, so we'll do it again. N equals 1. L equals, well, still an S. That's 0. It's still the same orbital. That's some M symbol is 0. And then it's going down this time. So it's a negative half. If it's up, it's positive half. If it's down, it's negative half. All right. That seems pretty simple, but we're going to make it harder. Okay. So we're going to go ahead and we'll do carbon. All right. We already did it. We'll do it again. 1s, 2s, 2p. 1, 2, 3, 4. Off ball. Fill the bottom ones in first. 5, 6. Hund's rule. Make sure they're in a different one. And then Pauli exclusion. Make sure one's up and one's down. Right? One's up, one's down. So we're going to do the L. We're going to do this one this time. Make it a little more difficult. We'll do that one. Okay? And maybe it's not more difficult. N equals, what's that number? 2. M or L, M sub L, and then M sub S, which we'll do right away. It's going up to positive half. Okay, now it's a P this time. Right? It should be a P. It's a terrible looking P, but it's a P, right? So its value for the L is 1. And then this is where it gets a little tricky because N equals 2. It has two possible shapes, 0 and 1, S and P. And this is negative 0 to positive 0, and this is negative 1, positive 1. So this one has 1 orbital, and this has 1, 2, 3 orbitals. So this would be negative 1, 0, and 1. They're just in orbit. So that electron would be 0. And therefore, we'd have all 4 quantum numbers. We're using orbital diagrams. All right. Let's look at the electron configuration for potassium. I have it on here. Movie somewhere. Like that. All right, here it is. All my junk piles starting to build up. Okay. So let's look at this one. Potassium, 19. And I'll find it on the table. We got all kinds of cool stuff to do here. Here's potassium. That's a 4. That's an S. That's 1 spot in. So potassium would be 4s1. Okay? But then it's everything that comes in before potassium. So what do I got to fill in here? Well, everything on top, anything in the lower numbers on the side. So that would be all of these, all of these, all of these, all of these, and the top row. So let's do this one first. 3P, 1, 2, 3, 4, 5, 6. Got to fill it. And then this one, 3S, 1, 2. 2 P's, 6. 2S, 2. And then 1S2. So then we end up with 2, 4, 10, 12, 18, 19. The top numbers should all add up to be the atomic number. So that's what we call the full, right? The condensed one is kind of like making it shorthand. It's called noble gas configuration. And what we do is because noble gas are full, their S and P's, right, will be full. We'll find the noble gas comes before number 19 on the periodic table. And these are the noble gases. And that noble gas is going to be argon. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. And you'll notice that these two are the same. So this is argon, What we'll do is we'll substitute in, instead of writing all this stuff all the way out, let's put argon, brackets around it, 4s1. And I'm pretty sure we still get 19, because we have argon, which is 18, and you add one more is 19. That's how you get argon. All right, so that's that one. And then it says draw partial orbital diagrams. We're only worried about the ones on the outside, so that's the 4s. How many electrons do we have? 1. So there's our partial. And our inner electrons are all right here. So the whole thing's 19, and I have 1 on the outside. That means there's 18 core electrons, or inner ones. All right, let's do the other one. We'll do technetium. Technetium. So that's going to be here. It's 43. Now I wrote on your 3D, 4D, 5D, and the reason why I did that is because when we started with this process, we had our nucleus, and then we had our tight ring, n equals 1, and then we had a big jump, and then what happened is the rings should be getting tighter. Rings get closer together. And in fact, there's overlap. I can spell it, right? And the first overlap goes on right here. Because according to our quantum numbers, if n equals 3, then I should have an L shape of 0, 1, and 2, S, P, D. So mathematically speaking, we do have a 3D. It's not here in the middle, though. It's actually dropped a level. So all of these are dropped a level, right? So they're never considered the outside electron. But anyways, ready? So if we're looking at technetium, there's 4D. That's where we're at. So we'll do the ending. 4D. And it's 1, 2, 3, 4, 5. So it's 4D, 5. And then we have these over here. This is 5s, 1, 2. And then we have, let's see, 5s, 1, 2. The noble gas comes before technetium is going to be krypton. It should be K-R. Like that. And I'll count to make sure. Krypton is 36 plus 2 more plus 5, all the top numbers, which is 43. So that's right. Okay, so that should be our shorthand one. I'm not doing the longhand one because there's no reason to do that. And then we'll do the orbital diagrams only for the ones on the outside that are not part of the KR. Then 5s, 1 up, 1 down. And then 4D. There's going to be 1, 2, 3, 4, 5. And we'll do 1, 2, 3, 4, 5. That's called Hund's rule. It's lower in energy to do it that way. Okay? So they're half filled. And that's technetium. And then lead, it's going to be a big one, right? So lead's over here. And you can see there's a space 56 to 71. So these ones go in there too. Right? But lead's number 82. And the noble gas comes over as xenon. We have Xe. And lead ends here, which is going to be a 6p2. So we'll put that way over here, 6p2. Can we see it? No, sorry, I'm right off the page. 6p2. And that xenon is the noble gas come forth, number 54. And then we get to fill everything that comes in between. So let's see. I have these over here, which I've written as a 5D here, and then there's 10 of them. So that means 5D10 goes there. And then I have to go drop down, because it says this is the space, and there's no room on the table, so they pulled it out. 4F. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 of them. And then there's these two over here, which are 6s, 2. So then I have a 54, 56, 70, 80, 82, which is what it's supposed to be. And then when I get crazy and I decide I'm going to draw these things, 6s, I'll draw them kind of the way I would going up in energy. 1, 2, 3, 4, 5, 6, 7. Right? And then one in each first, where you double up, but they're all going to be doubled anyways. They can't be the same direction because it'll violate Pauli exclusion principle. And this is the 4F, and then I'm running out of room. 5D, it's 5 of those. And they're all filled too, all in different directions if they're in the same orbital. And then 6P. 1, 2, like that. Oops, yeah. All right, and then we'll go back and just take a look at this one real quick. Okay. 8th electron, the F atom, so we'll take a look. And the third one, so we'll draw the orbital diagram out for it. With fluorine, it's small. 1s, 2s, 2p, right? 1, 2, 3, 4, 5. Right? There's 5. That one's kind of hard to see. That's annoying that I did that. All right, ready? So it looks like this. Okay. So what we're going to do is, like we already kind of practiced, I showed it to you. We're going to find this one and this one. So I'll do this one. I'll leave the last one to you. Right? So actually, yeah. So it's 2. N equals 2 because that number. L is 0 because that's an S shape. 0. There's only one orbital here, so the M sub L should be 0. And then it arrow's facing up. That's a positive half. Right? Half. And that's it. That's where we were. Okay? You didn't go any farther than that. I held off. Look over notes if there's something I didn't get. Make sure you let me know. That should be it for today.